In this video, we're going to bridge from our knowledge of transmission line power to electromagnetic power, and that'll be based on the video where we looked at V and I, and we went to E and H. And this is a circuit-based derivation, remember, a long time ago. So what we need, and we're dealing with phasors here, is the time average phasor power, P, which we know from circuits is 1/2 the real part of VI star. And this is assuming, of course, a time variation of e to the I omega t. And I keep wanting to do vectors. I've got vectors on the brain. So let's vector out of here. This is a scalar. However, when we go to fields, we have vectors. So let's see what happens. I'm going to assume that the power is also a scalar, and I'm just going to work by analogy. So what am I going to put in here, Sam?
Well, V goes to E.
V goes to E.
And I goes to H. Complex conjugate, yes.
So everything is great, right? We're done?
Something seems wrong.
What's wrong?
So E and H point in different directions, right?
Oh.
So if you just multiply them together, what happens?
Well, you'll actually get what they call a tensor. Like you'll get EX times HZ, and we don't know how to handle that.
Okay.
Or you get a matrix, really, which is a tensor. So we need to create something that, should it be a dot product or a cross product? So that's the problem here. Dot or cross for multiplying vectors.
So what we know is they point in different directions, and they do travel down the line in a third direction. So I guess a cross product, you can extract their traveling direction?
That's right, because we know from the previous video that the flow of power is down the line, right? Mm-hmm. The current is carrying the wave. We saw that there was a wave there, so there's energy in the wave. We know that from any kind of wave, ocean waves. So this has to be a cross product. And if it's a cross product, then this becomes a vector. Mm-hmm. And when we have a vector for the time averaged phasor power for fields, they don't use the letter P, they use the letter S. Mm-hmm. And the name for this is the pointing vector. And to finish off, it's always good to have the units. So what are the units of?
Just watts.
Watts, volts times amps. How about this one?
Watts per meter squared, because you have volts per meter. I mean, volts per meter and amps per meter, and you multiply them together.
Yeah, you multiply volts, amps, but each of these is per meter and per meter. Mm. So the units of this, are, this is the important thing, watts per meter squared. Mm-hmm. So it's, if you like, it's like a power density flow that's a vector, and it's carried down the line when we're thinking of fields. And this is useful, obviously, in transmission lines, but also in optics, in waveguides, in antennas. Very important. We must have the idea of transmitting power. Mm-hmm. So are we all done?
I think so, yeah, and I'm running late for lunch. So I guess I'll see you in the next video.
Oh, yeah, thanks a lot.
Okay, thanks. Have a nice weekend.
And you can see now that we have power.